Welcome back to God Maths. Mathematical literacy begins here. Today we will continue with our lesson on linear programming. Before we get started, I want you to understand these simple terms. Minimum or at least means greater than or equal to. Maximum or at most means less than or equal to, and exactly means equal to. These three terms will help us to formulate our linear programming model and effectively apply it. Before we continue with this lesson, don't forget to subscribe to this channel for more video lessons. Let's move on to today's examples. This is our first example for today. Now let's go through the question and see how best we can solve it. Casapreco Company produces two types of drinks, fizzy and alcoholic drinks. Each drink is produced at a station consisting of a machine and a person who finishes each product by hand. The fizzy drink requires 3 hours of machine time and 2 hours of finishing time. The alcoholic drink requires 2 hours of machine time and 4 hours of finishing time. The profit on the fizzy drink is 25 Ghana cedis per pack. On the alcoholic drink, it is 30 Ghana cedis per pack. If the work day is 8 hours, how many packs of each drink should be produced at each station per day to maximize profit? Let's go through the key points in this question. The question states that Casapreco produces two types of drinks, so we would have two variables here. Let's represent the fizzy drink by X and the alcoholic drinks by Y. So in our solution, first, let's X equal to number of packs of fizzy drinks, and Y will be the number of packs of the alcoholic drinks. Then we are told that the work day is 8 hours, which means that every day there is a maximum of 8 hours. And we have said before this lesson that maximum means less than or equal to. For machine time, each drink is produced at a station consisting of a machine and a person who finishes by hand. And we are told that for the fizzy drink, it requires 3 hours of machine time. And then the alcoholic drink requires 2 hours of machine time. And we have a total time of 8 hours per day. So for the machine time, we will have 3 hours for the fizzy drinks and then 2 hours for the alcoholic drinks. And that should be less than or equal to 8, the maximum number of hours we have. Then for finishing, for the finishing time, the fizzy drink requires 2 hours of finishing time. This is the finishing time. And the alcoholic requires 4 hours of finishing time. So we will have 2 hours for the fizzy, 4 hours for the alcoholic. And that is within the 8 hours required in the day. Then the profit on fizzy drink is 25 Ghana cedis per pack. So if there are X pack, then the profit will be equal to 25X. And the profit per pack for the alcoholic drink is 30 cedis. So if there are Y number of packs, then the profit will be 30Y. Now, our linear programming model will now be to maximize this profit. p equal to 25x plus 30y, and that is subject to the following constraints. The first is the machine time, which is 3x plus 2y less than or equal to 8. Then the finishing time, 2x plus 4y less than or equal to 8. Don't forget our non-negative constraint, which always hold, and that is x greater than or equal to 0, y greater than or equal to 0. Now let's look at how we can maximize this profit subject to the following constraints. As shown in the previous examples, we will change the inequalities to equations and then solve for the values of x and y. So our first equation, 3x plus 2y is equal to 8. That is from this inequality. And here, when x is equal to 0, we will have 0 plus 2y equal to 8, which will give us y is equal to 4. So our point will be 0, 4. Then when y is equal to 0, we will put the value of y there and have x is equal to 8 over 3. So our point will be 8 over 3 is 2.67. So 2.670. Then next we have for equation 2. Which is the second inequality. That is 2x plus 4y less than or equal to 8. So we have 2x plus 4y equal to 8. When x is equal to 0, we put the value of x here, and we will have y is equal to 2. That will give us this point. When y is equal to 0, we put the value of y here, and we will have x is equal to 4. That will give us 4, 0. So we have these 2 points for equation 2. 0, 2, 4, 0. And for equation 1, we have the 2 points 0, 4, and then 2.670. Don't forget our third equation, the non-negative. X is equal to 0. That is equation 3. And y is equal to 0. That is equation 4. Let's move on to the graph for these inequalities. On this graph, the blue line is the linear graph for our first equation. And then the red line is the linear graph for our second equation. Now, the non-negative constraints, x is greater than or equal to 0, will be on this vertical line. We have seen that in our previous examples. So this is x equal to 0. And then for y equal to 0, we will have it on this line. Now when we shape this graph, we can easily identify our feasible region. And the corner points of this feasible region are these points. We can inspect, by inspection, we know that this point is 0, 0. This point is already one of our points, and it's 2.670. This point is also 0, 2. then these points can be obtained on a standard graph. But we can also get a more accurate figure by solving the two equations simultaneously. The equations that give us this point, we can solve them simultaneously. And that will be, we have 3x plus 2y equal to 8. And then the other equation is 2x plus 4y equal to 8. When we solve this simultaneous equation, when solved simultaneously, we will have x to be equal to 2 and then y equal to 1. You can solve these two equations simultaneously. So our point here is 2, 1. The simultaneous equation gives us a more accurate figure. Now let's find our maximum profit by putting these corner points in our objective function, which is the profit function. So let's take corner points here, and then this is our profit, P equal to 25x plus 30y. The point we have 0, 0. The next point 2.670. The next one 2, 1. And the last one is 0, 2. Let's put this in our profit function. This gives 0. This gives approximately 67. The next one is 50, that gives 80. And the last one, this is 60. So from here, we will realize that our maximum profit is 80 Ghana cedis per station, and then these are the values that give us our maximum profit of 80 Ghana cedis. X is the number of packs of fizzy drink, and Y is the number of packs for alcoholic drink. So to optimize profit, for maximum profit, two packs of fizzy drinks and 1 pack of alcoholic drink should be produced at each station per day. We will take another example on this. Let's check our example 2 for today. This is our second example for today's lesson. Macro Farms Limited can purchase 2 types of fertilizer which contain the following percentage quantities. Type X, type Y contain these percentages respectively of nitrate, phosphate and potash. A certain type of crop requires a minimum of these quantities for nitrates, phosphate and potash, 150 and 40 respectively. Type X costs 10 Ghana cedis per kilogram and Y costs 5 Ghana cedis per kilogram. The company currently buys 1,000 of each type and wishes to minimize its expenditure on fertilizers. You are required to construct a linear programming model for the problem, solve the model graphically, and then find the minimum expenditure that can be incurred on fertilizer, and find the savings the company can make by switching from its current policy of buying 1,000 of each type to your recommendation from the linear programming model. Let's start with the first one, which says we should construct a linear programming model for the problem. We have done this in our previous examples. Note that these quantities are in percentages, contain the following percentage, and all these amounts are the minimum requirements. We have stated the meaning of minimum in the beginning of this lesson, that minimum is greater than or equal to. So let's formulate our linear programming model constraints. For nitrates, we have 18% in type X and 3% in type Y. 18% is 0.18 and 3% is 0.03. And that should be greater than or equal to minimum of 100. Then for phosphates, we have 5% in X and then 2% in Y, and that is subject to a minimum of 50. For potash, we have 2% in X and then 5% in Y, subject to a minimum of 40. So type X costs 10 cedis per kilogram and type Y costs 5 cedis per kilogram. So the total expenditure on fertilizer, let's use C for that, will be equal to 10 cedis of type X for type X, each type, and then per kilogram of Y is 5 cedis. This is the total expenditure on fertilizer. Now the company buys 1,000 of each type, but we want to use linear programming model to minimize this cost, and that is our optimization of the objective function. So our work is to optimize, that is minimize this cost function C equal to 10x plus 5y, subject to the following constraints. And the constraints are 0.18x, 0.03y, greater than or equal to 100, 0.05x, 0.02y, greater than or equal to 50, 0.02x, 0.05y, greater than or equal to 40. Do not forget our non-negative constraints. These constraints are part of the assumptions of the linear programming model. So let's move on to find our points and then plot them on the graph. For equation 1, these inequalities will all be changed to equations, and our equation 1 is going to be 0.18x plus 0.03y is equal to 100. That is equation 1. We have learned how to get points from these equations already. So by putting x is equal to 0, we will have y to be equal to, this is 0, so 100 divided by 0.03, and that gives us 3333.3. So our point here is 0. And then if y is equal to 0, we will have x to be, this is 0, so 100 divided by 18. That gives us 0.18 rather. That gives us 555.56. So our point here is 555.560. That is for equation 1. For equation 2, which is 0.05x plus 0.02y, you will have, when x is equal to 0, y will be equal to, this is equal to 50. So when x is 0, we will have 50 divided by 0.02, and that gives us 2,500. So our point here will be 0, 2,500. Then when y is equal to 0, we will have x to be, when y is equal to 0, this is 0. So we will have 50 divided by 0.05, and that gives us 1,000. So our point here will be 1,000, 0. Then for equation 3, which is 0.02 plus 0.05y, this is x, 0.02x, and that is equal to 40. So when x is equal to 0, y will be equal to, this is 0, so 40 divided by 0.05, and that gives us 800. Our point will be 0, 800. And then when y is equal to 0, we would have x to be equal to 40 divided by 0.02. That gives us 2,000. So our point will be 2,000 and 0. Don't forget our non-negative constraints, which are equations. So this is equation 2, equation 3, and then equation 4, x is equal to 0. That is our equation 4. Equation 5, y is equal to 0. That is our equation 5. So from equation 3, we have these points. The first one is 0, 800, and the second one is 2,000, 0. For equation 2, we have 0 to 500, and then 1,000, 0. For equation 1, we have 0, 3.3, and then the other point is 5.56, and then 0. We are now going to plot these points on our graph and then use that to minimize the cost that is incurred in buying fertilizers. Let's move on to the graph. This is a sketch of the graph for the objective function c and the point we had. So when plotted, we have the following lines. This is a line for equation 1, shown in blue. The one in red is the line for equation, that is equation 3. And black is the line for equation 2. Now when we shade these lines, you will see that they all move upwards. And it is so because the numbers are all greater than or equal to. In the equation we have greater than or equal to, greater than or equal to. So greater than moves upwards. In the previous examples they were less than, so they moved inwards. And so when we shade these graphs, the last one, shade it as this. The non-negative constraints also move in the same direction as in the previous examples. So you will see that our feasible region lies in the outside and is bounded by these points. One, we will call this point A. Then this is our feasible region. We have another point here. So Our feasible region has 4 boundaries, as can be observed, where all our shadings meet. Let's get these boundaries. The first one is a point we already have. So by inspection, this is 2000, 0. This is also a point we have. So this is our point B. And then our point C here. That is point D. This point is 3, 3, 3, and 0. In our previous examples, we realized that we can find these points by solving the equation for the lines simultaneously. So for point B, we will solve this equation. This point B is formed by this line and the blue line. So we will solve 0.05 x plus 0.02 y equal to 50, and then the other line is the blue line, which is 0.18x plus 0.03y equal to 100. We will solve these equations simultaneously. Then for point C, we will solve the 2 equations are for this line and then the black line. So we will have 0.02x plus 0.05y, and that is equal to 40. And then for this one, 0.05x plus 0.02y, that is equal to 50. Solve these simultaneously and get the following values. We have x is equal to 238.1, y is equal to, we have 1904.8. So our point B will be B 238.1, 1904.8. And then when we solve this simultaneously, we have x is equal to 809.5, and then y is equal to, you can use the calculator to solve it simultaneously and get these answers. So our point C is also C 809.5, 476.2. These are the boundary points A, B, C, D of our feasible region. Let's put that into our cost function and see the values we have. So we have the point here, the point, and then C equal to 10x plus 5y. Let's put the point there. Point A is 0.333, and that gives us C will be 10 times 0 plus 5 times. This will be equal to our point B, which is 238.1, 1904.8. So 10 times of this plus 5 times, and that gives us, so the first one is, then the second we have, you can always use a calculator. Our point C is 809.5, 476.2, and that gives us 10 times that. Then our point D, we have D here, 2000, 0. So 10 times 2000 plus 5 times 0. This gives us 20,000. And that also gives us 10,476. Approximately. These are approximations. Then, in our question, we want to optimize That is to minimize the cost. And so we will look for the minimum cost, which is this. And then the values of x and y that give us those minimum costs. So if we want to have the minimum cost, then our expenditure, question C says find the minimum expenditure. So C, minimum expenditure, is equal to the smallest amount we have here, 10,476 pesos. Then D, we want to look at how much the company can save by buying these quantities, which will minimize the cost. But previously, the company used to purchase 1,000 of each package. So let's find the previous cost. Or we can say savings will be equal to previous expenditure minus our optimum expenditure. The previous one is 1,000 of each. So x is 1,000, y is 1,000, which is 10 times 1,000 plus 5 times 1,000 minus our optimum expenditure is this one, which is 10 times 809.5 plus 5 times 476.2. This will give us, this is 10,000 and then 5,000, so 15,000 minus, this is our minimum cost, 10,476.00. So we can do this calculation and the savings will be 4,524 Ghana cedis. This is the amount the company will save when it switches to the optimum from our linear programming model. We will take 2 questions as assignment for this lesson, and when we meet in the next lesson, we will discuss those questions. So in our next lesson, we will discuss the solutions to these assignments. Try as much as possible to go through the questions carefully and solve it to the best of your knowledge. You are always free to contact us via our WhatsApp numbers provided in the video description below. Before you sign out, remember to subscribe to this channel for more video lessons. See you in our next video lecture.